In the previous video, we saw one implementation of the list ADT, which was the array. We also saw that arrays don't work well when we are trying to add or remove elements in the front. So now let's try to overcome that problem with a different way of implementation of the list, which is a single linked list. So how do linked lists work is linked lists are made up of node objects where a node consists of two different elements. First one is data, and the second one is a pointer to the next element. So basically, you have these node elements that are scattered throughout the computer memory. So you have all these node elements that are there in the computer memory, either in the stack or heap, and you connect these using pointers somehow, and they are connected in a linear fashion, which is you can reach from one node to another through a series of steps. So how typically single linked list would look like would be like, let's say if we have a single linked list with just one node, we have this value 10, and this is going to point to the next value, which might be something like 20, and then to the next value, which might be like 5. And we know that we have reached an end when there are no more values, which is like sometimes it's represented by this, which is called null, or sometimes it's represented by a final block which has this x at the end. So let's see how we can define a linked list in C++. So here we have this node object. Like first we have to, in order to build a linked list, we first have to represent the node object either in the form of struct or a class. I prefer the class terminology, which is in this case we have a class called node that has two different data members, which is next as well as data. Now, how we can build a linked list is by creating an object, which is, let's call it node n1, and then we can just assign n1 dot or n1's data to be some value, and then n1's next to be like either pointing to a null pointer. Like let's say if there was just one node, if there were more than one nodes, what we can do is instead of pointing it to null, we could point it to a new node. Okay, so let's call n1 also like new node, which is we are allocating this memory on the heap. And if we try to do this, so basically how this works is the first two statements will create a new node that will have, that's called n1, like n1 is pointing to this new node. And now n1's data, like whatever n1 is pointing to, its data is equal to 10. Now n2, which is like either you can do it in two steps, which is n2 is equal to new node and then assign the value. I'm doing it in one step, which is now n1 dot next. This can store a node next pointer, and now this is pointing to a new empty node in this case based on this statement. Now if we want to change the data or the pointer to the next element in this node, how we can do that is using this terminology, which is n1 next and then data, because n1's next will give us a pointer to this node, and if we want to change the data to, let's say, 30, this statement will change the data to 30. And similarly, if we are using n1's next and then next is equal to null, so this will make this pointer point to null. So this is how you can build a linked list in a naive way. Uh, we are going to discuss this implementation, which is like, again, like I have this int mean, I have a node star object. I missed a star here because in C++, whenever we create memory on the heap, it should return a pointer to the memory address in the heap. Next, we are defining object data equal to 10, and then object next equal to null pointer. So in this case, like these three lines would create a new node in the first two lines, which have 10, and the next value is null. Next, we are now going to create a new date, like this. Next is now pointing to a new node, as we did in the previous example. This has the value 20. Then in this three next set of statements, I'm doing objects, like this is the object. Objects next is equal to new node. So it's creating another new node. Now the value is 30. Finally, we are storing objects next, and then next value to a null pointer. So the final list is pointing nowhere, or the final node in this linked list is pointing nowhere. But this is a very naive way to build a linked list, because you see, like, we are again and again trying to add like this next pointer, and it gets pretty irritating. Like, we don't want to do this. Like, we want to more abstractly do the same operation in a single linked list. So how we can fix that issue is by having like a parameterized constructor. And in this case, I have a new parameterized constructor called node that takes in the data as well as the next. And what this does is it changes the data to some value that we are passing, and the pointer to the current node next to be the value that we passed. So in this case, I have my int main, and I just created a new node in the first line. So basically, obj will now point to a new node that has value 10 and the value null in the first line, which is this line. Next, I'm passing like I'm now creating a new object, which is again, I'm calling this obj, because this obj is storing kind of like a head of the linked list, which is we have the head that's being stored in the object. And now I pass 20 and obj in this constructor. So when I pass this 20 and obj, like this, into the constructor, what this does is it changes the current objects, or it creates a new node with the value data equal to 20. So we have this new node where the value is 20. And since we passed the original object into this linked list, we are going to change the new node's next pointer, which is this one, to the object, which is, in this case, it's pointing to this. So what we are trying to do is we are creating, or we are adding elements in the front of the list. So when we call this 30, you'll see that we are basically calling we are creating the new node with value 30. And since we are passing the object, which is now pointing to 20, so the next pointer will now start pointing to this 20. So basically, we are trying to add numbers in the front. But again, there are several issues with this approach, which is we are again and again passing this object. And this is like whatever we have discussed so far. Like, let's say if we are building different functions like add or replace, remove in a single linked list in this way, this is called something called naked linked list, because we are still not abstracting the details that are present from the user. So a user cares about something like this, which is if they have a linked list object, they want to just like add some numbers, or they want to do something like what is the value, or like they want to get the number at, let's say, the position 5 or something like that. But here we are still passing this object value, which is we are again and again calling recursive calls on the head of the linked list. Now, in some languages, this can be avoided. Like, let's say if we are doing functional programming, this is absolutely fine. But let's say if it is C++, there's a high likelihood that the programmers will screw over the manipulation of pointers. So we want to abstract all the details of the pointers from the user. And that brings us to another design of the linked list where we basically abstract this node or encapsulate this node in another class, which we are going to discuss very soon, uh, called linked list, and then make a node object inside this class, like either using inner classes or using a separate struct. Either way is fine. So in this example, for the previous case, I just built another method just to show you like how to calculate the size of the linked list. It's pretty straightforward. I'm going to discuss that very soon. But basically, like let's say if you have that object that was pointing to this linked list like 20, 30, and there's another one like 10. So let's say if you pass that object which we discussed here into the size method, which we just built, an easier or intuitive way to build the size is using a recursive approach where I built the size method. I have built like several methods. You can look at it at this link. I'm not going to discuss that in the class because we do have like just finite amount of time. But for the exams and stuff, you should know, like let's say if we tried to ask you how would you add an element to an array or single linked list or any of the types of linked list, you should be able to at least perform simple instructions like add, remove, count, and a few other functions which we are going to discuss very soon. But in this case, if it's we are calling the size parameter, it's checking the base case for this particular function would be if the object is pointing to null, which is we have an empty linked list, so then it returns 0. Otherwise, it returns 1 plus. Instead of object, now we are passing uh, objects next, which is in this case, you're just passing this half of the linked list by using this is the current object, so this next will give this particular linked list, and then you're calling the size method again on that particular object. So again, when we were talking about designs, we discussed the fact that there's a high likelihood that the recursive implementation of the node linked list class, which is like if you have a naked linked list, it could be pretty dangerous for both the user as well as for the programmer, because there's a great chance like if you're building more sophisticated functions, the programmer might somehow make a lot of mistakes. So the best way to implement linked list, as you're going to see in different languages, probably I'm just talking about Java and C++ right now, is to have a new class which is this node either embedded. So I have this templated linked list. So you either define a struct node or a class node. You can also move this struct node or class node right inside this function in the list class. So we have a templated list in this case. I also have like two different pointers. One is called the head and the other one is called the tail. We are going to discuss the tailed approach a little in a little while, but basically you have a head that is always pointing to a linked list, and the user only has access to the linked list objects and they don't know what these head and tails are. Note that all of this is in form of private data members, which is we don't want users to access any location in the memory. So we have made all of these variables private, which is we have encapsulated these details, and the user will just create a new list by calling something like list obj equal to new list or whatever, and so on. I'm using templates, but if you want to simplify this, you can just use like a certain type. But it's always always good to use a generic template based list because you can store any particular types of objects. So in the constructor, I'm basically calling a new list with the size of creating a new list with size 0. Next, I'm creating new nodes for head and tail. So for an empty list, there'll be two just nodes. and heads next would be pointing to this tail. So we do not have any particular values in these nodes. This is another way to there's another way to design this, which is you have like sentinel nodes. What are sentinel nodes is basically they don't store any data for the first value, which is the head does points to a node which doesn't store any particular value, and that is used in some of the functions. We are not going to go into that much detail, but in this case we also have, like in this case, I designed a new function called push front, which adds an element to the linked list. So we are going to discuss that, which is, let's say if we are trying to add an object, we create a new node, we add the data to this new node that we just created. Next, we change the queues next, which is, let's say if it was empty, like let's call this head, let's call this tail. Head is pointing to tail. So if we have, in this case, queues data, like we created a new node queue, and let's call x like 10. So we created a new node with q equal to 10. The data is 10. And queues next pointing to heads next, which is this element is now pointing to tail. And then heads next is equal to q, which is heads next is this one. And this is now pointing to q. So basically, we added a particular element in the front. And similarly, if we try to do it again, like let's say if we create a new object with a value 20, and if we try to add that, again, we follow the same approaches and it's going to add a value 20 in the front. So let's discuss the characteristics of a single linked list. We are not going to go into depth in other forms of linked list, but I just wanted to give you a brief overview. Again, I'm like telling you, you should know how to add or remove elements in the linked list. Since we have like finite amount of time, I won't go into depth for each of the functions. So let's talk about the single linked list characteristics. So again, like lists consist of nodes which contain data as well as pointer to the next node. There might be a head node. It's usually the case that we always have a head node. There might be a case where we may have the tail node. So right now we are describing the characteristics of just the single list, linked list without head, without tail, sorry. So again, it stores similar elements and they are stored in memory but non-contiguously, which is, let's say one element is here, the other one might be somewhere different place in the memory, and the third one might be completely different. So it does not allow random access, which is like, since we don't know where the since the elements are not contiguous, we cannot do something like what we did in array, which is you cannot do something like what is linked list of 5. If you have to do that, you have to overload this square brackets, or uh, you have to find, like if you want to manipulate the random access, you have to overload this operator. I've actually overloaded the operator in the URL that you have here, so you can see how to overload that, but I'm not going to go into detail. You should not know that for the exams. Like all the C++ specific things you do not know need to know for the exam, you can always write like pseudocode. But we are going to test those competencies, which is whether you understood like how to build iterators or use these C++ concepts through either the quizzes, or you have to ensure that you're learning all those things by the stepping problems. Let's talk about the operations. So list APIs typically, like I'm just talking about linked lists, uh, they typically have a good set of functions, which is like you can add some values. Now, addition takes place by two different ways, which is either you are adding in the front or in the back, which is you have this push front method and you are adding some key in the front. You have some push back and you push some values in the back. Next one is removal, where you remove an element from the front. The next one is access, where you get an element from the front or back, which is you cannot just access any particular element in the middle. Again, you have to build some function for that. But if you are trying to access just the first element or the last element, these are the functions that are given to you. Another set of functions is the find function, which is you have some linked list, you are trying to find some value, how you can find that. Next one is erase, you have some key and you want to delete that. The last one is empty, whether the list is empty or not. Also, we have this add before and add after in some of the APIs that's implemented, which is we pass a node and a key, and we want to find out whether we want to actually add a new node right before this node with the value key. And similarly, the add after works with you have some node object. In this case, a lot of APIs actually pass in iterators. We are going to discuss iterators very soon. You pass in the key, and your job is to find out whether this will to add a particular key, like you create a new node with this key value, and you add this node right after the node that you are passing into this function. So let's discuss performance for this. So in this case, we have all these methods. We have push front, pop front. So let's discuss it one by one, which is, let's call it push front. We have this, I'm just drawing this, which is we have this head that's pointing to a node, and we have some linked list that's growing indefinitely, or somehow we are growing this. So what about the push front operator? Now, since we have access to head, this would be a constant operation because we just need to manipulate two pointers, which is we create a new node, we point our head to this node, and this new node's head next would be pointing to the original head. So that's why it's O1. Similarly, pop front would again be O of 1 because we have access to the first element. Top front will also be O of 1 because again we just want to uh, get the value that is the first element in the list. So since we have access to the head, we can always do that in constant amount of time. Next one is find. So let's say if you want to find some value, uh, assuming the list is not sorted, like it's randomly sorted, it's a simple linear search, so it would take like O of n time. Next is pushback. Now, when we are talking about the single linked list without tail, we do not have access to the tail element. So if we want to add an element in the last, we need to traverse the linked list from one place to another. Like if you have a linked list object, again, I'm reminding you, I see a lot of students do something like linked list length -1. Like this is not allowed. You have to traverse the linked list by having something like a while loop. You have the head pointer, and within the while loop, you are doing something like head equal to heads next. So in case of pushback, it would take O of n time because we still have to go to the last element. Similarly, for pop back, it would take O of n elements because we still need to traverse. And the last one in the back series is the top back, which is again, if we want to retrieve the last element in the list, it would be O of n complexity. Let's say if we want to erase some value from our linked list, we need to first search that value, right? So again, like this is completely dependent on find function, and then the removal might just take constant operation. So it would be something like O of n. What about empty? This should be O of 1 because we'll just check if head is equal to null and we stop. And then we have these two different functions, add before and add after. So if we have access to the before one, like let's say if we talk about add before, we cannot do that, which is like, let's say if you have access to this node. Now, if you want to add a node right before this, the pointer is actually pointing in this direction, which is it's on the right hand side. So you still have to find where this node is in the list because you need to have access to this particular element, which is like you still need to access where is this particular location which is right before that. So you have to still traverse the entire list to find out where the node is existing. So it will be again O of n, and add after is O of 1, because we know, okay, we have this node, we can just manipulate the next pointer to find a value in the linked list, to add a value after a certain node in the linked list. So again, like we saw the all these three operations were O1 and n. All of these were On, and finally this was On, and after was 1, as well as empty was 1. So let's discuss the benefits and drawbacks of this approach, or using a single linked list. So the benefits include, like, adding and removing is way faster. Like when we were discussing arrays, this was O of n's, but now it's O of 1's, as you can see here. What about the drawbacks? Now, the first drawback is pretty obvious. Now we are storing pointers, so we are basically storing more memory. So all of this is like more expensive in terms of memory. But what about drawbacks in terms of time? So in this case, the random access will be O of n. Like, let's say if I want to find the fifth element, I want to traverse the list from 1 to n, where n is 5 in this case. It's trivial, but let's say if it was a billion, I would be traversing through the entire list. Also, these functions, top back, push back, or adding something in the back of the list, is very expensive. So that, to solve this particular issues, like these drawbacks, we are going to see other three different types of linked list in the next video.